Welcome everyone. We are now going to begin a series of our online lectures for the Intelligent System course. We are going to cover topics that I intended to discuss after the midterm. So we're going to start with the particle and Kalman filters. So what are these particle filters? So I would like you to recall the robot tracking problem that we discussed before the midterm. So we wish to track a robot which is moving in some arena. So for example, here in this case, if a robot wants to move from, let's say, point X to somewhere in the vicinity of point Y, then we need to come up with what we call as the robot motion model, and we are going to come up with some guess. So the simplest guess would be that the robot is going to follow a straight line motion. So it's going to go from point X to somewhere close to point Y by following a straight line, right? And so this is our guess. Now particle filters, they play a very important role in a sense that they are going to refine our guess using sensor information. And in this case, our sensor, you can think of our sensor as camera. So camera is going to take snapshots of the robot at regular intervals, and that is going to help us refine our guess. Let's see how that is going to happen. So our guess is the robot is going to move in a straight line. So that's one possibility. But suppose that in reality the imperfections in our robotic system, maybe the actuators are somewhat faulty, or the sensors are a bit noisy. It is possible that your robot diverges from the straight line motion, and the actual position of the robot as it moves from point X to point Y diverges from the position, from the expected position had the robot followed a straight line motion. So a robot starting to move at time t has an actual position which is very different from the estimated position at time t plus 1. And so this difference, however, can be reconciled by the sensor data. So remember, the sensor in our case is the camera, and it is going to guide us towards a better estimate. But remember, the sensor, the real-life sensors, as we all know, can be noisy. So here our problem is posing a double trouble. The first problem is that our guess about the robot motion model can be somewhat inaccurate. And the second problem is that our sensor can be noisy, and because sensor is directly observing the robot position, so we want it to be as accurate as possible. But in reality, the sensor information which we would have liked to use to refine our guess, that may also be less accurate. So what particle filter does is that it helps us find middle ground between the motion model inaccuracy and the sensor noise. So we have to find a middle ground. And as you can expect, the best guess you can come up with will be the one in which this middle ground has been followed. So one way to do it is that we generate multiple images based on robot motion model, and then we try to match those images with the real time or the real images taken by the camera. And so there are two types of images here that we are talking about. One of them, you can think of them as the virtual images. Those are the images that we generate based on the robot motion model, that is based on our visualization or the way we think the robot is moving. And those images are going to give us the information based upon our guess. It's a guesswork. And then there is another set of images which are the images taken by the camera, and the job of the particle filter is to somehow find the match between the two set of images. And it is going to do that by discarding the virtual images, that is the images which are based upon our guess. We are going to discard some of those images which are not consistent with the images taken by the camera. And a slight change of terminology. So I'm going to replace images because image is eventually going to be used to extract the location of the robot. So instead of using images, I'm going to use the word location here. So what we're going to do is that we are going to generate multiple likely locations based upon our motion model, our guesswork, and we're going to match them with the locations obtained from the images, from the camera images. Alright, so I'm going to denote the location by a circle. And the robot location at time t is shown by a circle. So the horizontal axis represents time, and we're saying that the robot is located at some position indicated by a small circle at time t, and we are going to make a guess about the robot position at the next sampling time, let's say t+1. And because we are not sure if our robot motion model is perfect, there is some element of uncertainty. So we are going to assign multiple locations at time t+1. So we are going to say that our robot can be any one of these locations at time t+1. Here in this diagram I have used 5 close by positions, and so they are representing different possibilities indicating the robot location at this time instant. In the taxonomy of the particle filters, we're going to call these circles as particles. So from this point and onwards, we're going to refer these locations, we're going to refer particles to describe the possible locations of the robot at any given time instance. And by the way, these are known as particles just because they look like particles. That's why the name particle filters. So in some sense, these particles indicate different possibilities. And because our models are all probabilistic, so therefore these dots represents different possibilities, hence the particles. So again, I think the idea over here is that if you have a particle at time t, which means that we have some knowledge with some, obviously with some probability of a robot location at time t, it will translate into multiple locations at the next time instance, which in this case is t+1, and that comes about because of the robot motion model, which may not be perfectly accurate. Now, how we are going to process these particles? And note that our guide here is the camera, the sensor data. So you see this blue dot representing the location. This blue particle is representing the robot location as told us by the camera image. Whereas the black particles, they are representing the robot location based upon the virtual images. That is, the images based upon our robot motion model. And right now, I have purposely shown all the particles with more or less the same size, but their size in the next few slides is going to convey a very important message regarding their significance and the weight. So right now, all the particles, you can think of all these particles as equiprobable robot locations. So the robot can be any one of these black locations, black particle locations at time t+1. All of them are equally likely. Now the question over here is that we have two set of particles here, one of them based upon the robot motion model, the black ones, and the blue one is the one obtained from the camera image. And both particles, they carry some level of uncertainty, either due to the robot motion model or the noise in the sensor, which in this case is the camera image. Now, the question over here is that we have about 7 particles, and we have to make a guess. We have to come up with an estimate of robot position at time t+1. So which of these 7 black particles are representing the robot location more precisely? So we need to have a method of gradation. We're going to assign a grade or a weight to the particles based upon their contribution to the estimate. So some of these particles will be representing the actual position, or will be representing an estimate of an actual position of the robot much better than the others. So the question is, which particles provide better estimate of robot location at time t+1? And we're going to answer this question by using a reference, and the reference is the camera, the robot location obtained from the camera. So the way particle filters work is that it is going to select particles which are closer. So it is going to select the black particles for higher weightage which are closer to the blue particle. So you see the top 2 black particles, they are closer to the blue one, and so they are going to receive higher weight. So it means that, in other words, the particle which are closer to the sensor data are more accurate in estimating the location. That is the message. And likewise, the particles which are away from the sensor data, they are going to receive lower weightage in the overall estimate. And so I'm now going to change the size of the particle in proportion to the weight, to their relevant weights. So as you can see that the particle closer to the blue one have been enlarged, and the particles which are away from the sensor data point their size has been shrunk, and they have received, they will contribute less towards the overall estimate. And so this way particle filters, they are going to give us an improved estimate. And this whole process is also a kind of filtration. So we are filtering out particles which are less relevant to the estimate, and we are keeping those particles which are more relevant to our estimate. So if I want to describe how particle filters should be implemented in the software, here is a summary or a pseudocode. So you start with n particles of the state variable xt. Now, so what do I mean by this statement? By that I mean that because the state xt is a random variable, so I'm going to take n samples of these random variables, and I'm going to call them particles. In the next step, I will take each particle and transform it to new particles according to the the motion model, which is actually the conditional probability of the state variable x at time t plus 1 given state variable x at time t. In the next step, we are going to assign weight to the transformed particle, and the weight is again a probability. So this probability comes from the sensor model. So this is probability z, which is the sensor output at time t plus 1 given the probability of the state variable xt plus 1. In the next step, we are going to calculate the probability of the state variable x at time t plus 1. So therefore, this is probability x t plus 1 from the weighted sum of the transformed particles. And this completes one iteration of the particle filter. But if you look at the last line, it is going to give you a clue which is analogous to what we said in the first line, that for the next iteration we are now going to work with the particles, n particles of the state variable inferred at time t plus 1. So we are going to sample and take n particles from x, state variable x at time t plus 1, and we are going to continue to repeat this process till the time index of our interest. So we're going to look at a specific example, and for that it will be helpful if you can recall the Bayesian network. By the way, particle filters is a way to solve Bayesian network, a special type or a class of Bayesian network that we call as dynamic Bayesian network. So I hope students are familiar with the diagram and all the exercises that we did before the midterm. So if you need to refresh, I would strongly encourage to brush up on your knowledge of the Bayesian networks. So just to summarize, the state variable, in this case we have just one state variable, that is x, and the subscript indicates the time index. So x1 represents the value of state variable at time t1, and x2 represents the value of state variable at time t2. And z represents the sensor output. So z1 represents the sensor output at time t1, z2 represents the sensor data, sensor output at time t2. And there's an arrow between arrow from x1 to z1 because the sensor is actually measuring the state of the system. So in this construction, our job is to calculate the probability of the state variable at time t plus 1 from the probability of the state variable x at time t, as well as the new sensor information that has just arrived, z t plus 1, and we're going to use particle filters, and we're going to take 10 particles in this example, and we're assuming a prior probability of the state variable at time 0, that is probability x0 is equal to 0.5. So as I had described, our step 1 will be to take samples of x0, right? And by the way, as has been our convention, we are looking at a very simple problems where the state variable can only have two values, like true or false, 1 or 0, like it's a binary state variable, and the sensor can also has only two values, true or false. So in this case, we're going with true and false only. Both the state variable and the sensor output variables that they are binary variables. I have listed 10 particles. These are obtained from sampling the state variable at time t is equal to 0. So as you know that x0 could be true or false with the same or equal probability, that was 0.5. So it's like flipping a coin 10 times. And so suppose, like in this example, suppose you get 6 true samples and 4 false samples, which means that out of 10 samples, 6 of them are true, the other 1 are false. Now in step 2, we are going to transform these particles. So we are now going to make a guess how these particles look like as they go from time t0 to time t1. And we are going to do that for all 10 particles. So here we are going to employ motion model. And if we look at the probability describing the motion model, then there is an 80% chance that if the particle is in true state, it will remain in the true state at the next time instance. And if it is in the false state, it can be transformed into true state with probability 0.3. And similarly, the other two probabilities going from true to false is 0.2, and to go from false to false is 0.7. So these are the probabilities that we have assumed. So you see that, and you can expect that most of the particles will not change their state. And there are, in this example, I have chosen 2 instances where the flip has occurred, because there is 30% chance that a false particle becomes true, and a 20% chance that the true particle becomes false. And so out of 10, you can expect that 2 or 3 particles will change their state. So for example, in this case, particle 8 and particle 2 has been flipped. The next step is to assign weight to the particles, and we're going to use the sensor model probabilities. The probabilities that we have used here say that if a particle is in false state, then the sensor tells us that it is in the false state with 80% chance or probability 0.8, whereas the sensor output is opposite to the state of the particle when the particle is true. That occurs with probability 0.4. And you can calculate the other two probabilities when the sensor output is true by yourself by subtracting these probabilities from 1. And so we're going to look at the column x1, and wherever you see false, you will put 0.8 against the weight, and wherever you see true, you are going to put 0.4 as the weight, and you are going to fill up the whole table with the weights. So the true particles are going to have weight 0.4, and the false particles will have weight 0.8. Now the total weight of the true particles sums to 2.4, and the total weight of the false particle sums to 3.2. And this is based upon the observation. So we say that, or we're given that the sensor output is false. So maybe I should have said it in the beginning of the slide. When you are about to assign the weight, you have to look at the given sensor output or the sensor data. Is it false? Is it true? So in this example, the sensor data is false, and therefore you are going to choose the weights accordingly. You're going to choose probabilities with Z1 equals to F. Now had you observed a different sensor data, that is for case Z1 equals to true, then obviously your weights would have been changed, and I guess those would have been 0.2 and 0.6 respectively. At the last step, you're going to calculate the probability of x1, that is the estimate or the likely value of the state variable at time t1. And the way we are going to do is that we're going to divide the total weight of the true particle by the total weight of all the particles. So remember, if you sum up all the weights of all 10 particles, you are going to get 5.6. So the probability that your particle is in true state, let me say that again. So the probability that your state variable has true value at time t1 is 3 over 7. Similarly, the probability that the state is false can be calculated by the sum of the false particles, that is 3.2, divided by the overall sum, that is 5.6. So this turns out to be 4 over 7. So this is the last step of one iteration of the particle filters. So our initial estimate was saying that the state variable was equiprobable, true and false. But now, at time t1, the estimate has changed, and this estimate is favoring the state to be in the false state. This is because the sensor output was false. So therefore, the estimate is uneven now, in a sense that the probability that the state variable is in false state is higher than the probability that state variable is in the true state. Now, had we seen or observed a sensor output as true, then this estimate would have changed, and I would highly encourage all the students to repeat that exercise for the sensor output, that is Z1 equals to true, in the last slide. So again, you can proceed to the next iteration, and I think that can be done as a homework exercise. The next instance, you can assume that the sensor output is false, and you can repeat that procedure and come up with the estimate at time t is equal to 2. So let me know if you have any concerns or questions in this example, and hope we can always discuss the problems in the subsequent Q&A session. So we're going to summarize the merits and demerits of the particle filters. It's a very practical, reliable tool of state estimation of real-life systems, which can be modeled as Bayesian networks. It is general enough and can be applied to nonlinear systems, that is, systems in which the motion model is described by a nonlinear systems. And it is also applicable to systems containing non-Gaussian sensor noise, and I'm going to explain that in a bit. But one downside or one demerit of the particle filter is that it incurs a high computational cost. In order to have an accurate estimate, you need to work with large number of particles. And we saw that in our example, we saw that we had about 10 particles to estimate a state of a binary state variable x. Now imagine if you have large number of state variables to track, and they can have more than 2 possible values, and then the computational cost and the complexity will increase tremendously. So considering that demerit, people came up with a more efficient solution, although that has restricted applicability, that is Kalman filter. So Kalman filters, some of you may have a very good idea already. They are generally applicable to continuous time linear systems. So that's the main difference. You see, particle filters can be applied to nonlinear systems, but here we are constrained to use linear systems. The sensor noise in Kalman filters needs to be represented as normal random variable. So that's the second constraint. The third constraint is that the uncertainty in the motion model should also be modeled as a Gaussian or a normal random variable. So if you're not familiar with this notation, that I have shown on the left hand side, the probability zt given xt and probability xt plus 1 given xt, that is basically representing a Gaussian random variable which has two parameters. The first one is the mean, so the mean in both cases is xt, and then the second parameter represents the variance. So the tracking, again recall the robot tracking problem. So we start with some guess. Again it is about guess, and this time we're going to represent our guess not by discrete circles. We're going to use continuous random variable, and more specifically it is a Gaussian random variable. So you have an estimate of xt represented by a Gaussian random variable whose mean is mu of t and whose variance is sigma of t square. Now the physical interpretation is that we are saying that our robot location is very likely near mu of t, but because there is somewhat uncertainty which is involved, so we have some variance sigma t square, but the mean value of the robot position is mu of t. Right. So this is our knowledge of the robot position at time t, and now we are going to evolve this estimate and see what is the location of the robot at the next sampling time. In this case it is t plus 1. And so suppose our estimate at time t plus 1 is represented by the state variable x t plus 1. So we are saying that at time t plus 1 the mean position of the robot is mu t plus 1 and the variance is sigma t plus 1 square, or sigma square t plus 1, depending upon how you are going to pronounce this. The main question that Kalman filter is going to answer is that it is going to calculate the value of the mean position at time t plus 1 and the variance at time t plus 1 based upon mu t and sigma t square. So again we are given three types of probabilities. Sensor model, again represented by a Gaussian random variable. The motion model, again a Gaussian random variable. And the estimate, the current estimate probability xt, again represented by Gaussian random variable. So Kalman filters, they revolve around the Gaussian random variable. And because we have restricted our random variable to only one type of random variable, it is particularly useful to produce the closed form solution of the estimation update. So you can think of the particle filters as like a generic solution based upon numerical scheme, and you can think of Kalman filters as an analytical solution which has restricted applicability, a closed form solution that comes at a cost of certain constraints. So we're going to estimate mu of t plus 1, that is the mean position of the robot or any moving object that you wish to track at time t plus 1, and the variance at time t plus 1 using the information of the previous mean and the previous variance of the estimate, that is mu of t and sigma t square, as well as the variances in the sensor noise model, sigma z. So sigma z in a sense represents the magnitude of sensor noise. Higher the variance sigma z square, larger is the sensor noise. And we're also going to use sigma x square, which is the variance in the motion. Variance representing the magnitude of uncertainty in the robot motion model. So higher the value of sigma x square, larger is the uncertainty in the motion model. So after doing some mathematics, which you can find in the textbook, I'm going to write down the end result that we want to discuss over here. That mu at t plus 1 can be written in the form of sigma t square plus sigma x square multiplied by zt plus 1. Now what is zt plus 1? Zt plus 1 is the sensor output at time t plus 1 plus sigma z square mu of t divided by sigma t square plus sigma x square plus sigma z square. So all the variances, they are added up and appear in the denominator. The update of the variance of the estimate at time t plus 1 is basically the sum of the variance of the previous estimate, that is sigma t square, plus the variance in the motion model, and the sum is multiplied by the variance in the noise model, sigma z square, divided by the sum of all the variances. So this is a nice succinct representation of the estimate update. And once we know the mean and the variance, you know very well we can specify the complete Gaussian random variable or its density function. So these are the only two parameters that we need to update at each subsequent sampling time, and to record or to estimate the position of the moving object. So a comparison between the particle, well actually before that, before the comparison, explanation and the interpretation of the expression that we have just discussed. So remember, sigma z square is proportional to sensor noise, and sigma x square is proportional to the uncertainty in the motion model. And the expression have been reproduced over here as well. How we are going to interpret this update of the mean and the variance? Well, there are two cases of our interest. The first one is when you have sensor noise much higher than the uncertainty in the motion model or that in the previous estimate. So case A, when sigma z square is much larger than sigma x square plus sigma t square, which means that in the denominator of both the expression we can approximate the denominators by sigma z square in both cases. And if you simplify this expression, you are going to get the mean, the estimate of the mean, that is mu t plus 1, approximately equal to mu t, which means that the mean location hasn't changed over time, or the estimate of the mean location is not going to change over time if your sensor noise is very large. And this is a very interesting result, because it says that if your sensor is very noisy, then you are going to trust the motion model more then you trust your sensor. So therefore, if you trust your motion model, then you are going to stick with the old estimate of the mean position of the robot. And likewise, the variance update in this case is approximately equal to the variance of the estimate at the last step plus the variance in the motion model. Now the case B, when the sensor noise is very small in comparison to the variance or the uncertainty in the motion model or the previous estimate. So the case B is the one in which we are working with small sensor noise but large uncertainty in the motion model or in the previous estimate of the state variable. Now, if you use this approximation then and simplify the expression, you will find out that in this case our estimate of the mean mu t plus 1 is approximately equal to zt plus 1, which means that we are trusting our sensor more than we trust our motion model, and the variance is approximately equal to the variance is the sensor noise. So to summarize, if your sensor is very noisy and your motion model is more accurate, then your estimate is dictated primarily by the motion model. And if your motion model is less accurate or very inaccurate and your sensor is very reliable, then your estimate will be dominated by the current sensor output. So these are the two important lessons that we can understand from the expressions given by the Kalman filters. A brief comparison, and I think some of these have been discussed already. The Kalman filters are going to give you closed form expression for the state estimation, whereas the particle filters are more numerical solution based. But Kalman filters have restricted applications where all the uncertainties are modeled by Gaussian random variables, whereas particle filters are applicable to wide array of systems where uncertainties can be represented by random variables which may be non-Gaussian. Kalman filters are only applicable to the linear systems. Particle filters are applicable to nonlinear systems as well. But Kalman filters have a nice closed form solution and they incur low computational costs. You know, the expression can be calculated very quickly and efficiently. But particle filters, you need to work with large number of particles and the numerical computational cost can be very high in practical settings. So that's what all that I wanted to discuss in this week's lectures. So I would encourage all the students to come prepared with your queries and the questions that we can discuss in our question and answer session tomorrow starting at 3:30 p.m. So take care and I'll see you tomorrow. Thank you very much.